And more generally, it's going to send x to the n to this summation over with binomial coefficients and just something that almost looks like the binomial theorem. So in this setting where you have algebras, and then you also have a coalgebra map, and this turns out to be an algebra morphism, then that is the definition of a bialgebra. So that's all you need for a bialgebra, ignoring some unit and co-unit conditions. And the conclusion here is that these two objects are dual bialgebras via this form. And so I'm going to leverage, so this kind of statement contains actually a lot of content. It's saying, well, you have things you can multiply, and then you have a form, and if you define these coproduct maps, then it turns out that there's this morphism condition. So this kind of lets us define bialgebras and Hopf algebras without having to talk about coproducts sometimes. I can just tell you two algebras and a form, and I can say they're dual bialgebras. So what's the difference between a Hopf algebra and a bialgebra? So a bialgebra is just something we have a product and a coproduct. So this is the lightning introduction to antipode maps. So if you think about linear maps from your bialgebra to itself, it has a natural product. I mean, more than one natural product. But we have this one called the convolution product, which is going to bring together all of the maps we have available. So we're going to first apply delta to turn something in H into a tensor, and then we're going to apply F1 to the first factor and F2 to the second factor, and then we're going to multiply them together again. So one first kind of interesting exercise to do with this convolution algebra is to note that the identity map on H is not the unit for this algebra. The unit is instead the composition of the unit and co-unit of H, which I'm not really going to talk about in this talk, because in all of our examples today, H is going to be some set of formal power series, and this composition is always just going to be the map that sets all the variables to 0. So it's this very simple object. So what is the antipode? You take this identity map on H, which belongs to the set of endomorphisms, if it has a two-sided inverse for this convolution product, meaning S times the identity map is given by this composition, then your bialgebra is a Hopf algebra. So if S exists, it's unique, and it's an algebra anti-automorphism, which means if you have a commutative algebra, then it's going to be an algebra automorphism. And our two examples here of polynomials and formal power series are Hopf algebras where S is the algebra morphism that just sends x to minus x. So that's a very pleasant exercise. You can check this convolution product. When we do this delta, we get this sum over I plus j of this binomial coefficient, and we had x to the I tensor x to the j. Well, the identity map doesn't do anything, and S turns x into minus x, and suddenly you have this formula x minus x to the n, which is indeed just setting x to the n to setting x to 0 in this expression. So it's usually 0 unless n is equal to 0. Okay, so this is our sort of general setup. So now I want to talk about some specific combinatorial Hopf algebras that are already implemented in Sage. So there's this convenient term of a packed word. Is just a finite sequence of integers with the property that if you look at the set of letters, it gives you all of the numbers 1 up to n for some integer n, which is going to have to be at most the length of your word. So there is a natural shuffle or shifted shuffle product on packed words, where you take two packed words, you extract the maximum letter in your first word v, you then shift up all of the letters in W, and then you shuffle V and W in all possible ways, and you take the formal sum of the result. So in this little example, we have 2, 1 shuffled with 1, 2. Well, 2, 1 is present in all of these terms in the same order. 1 and 2 are shifted up by 2 to become 3 and 4, and then they're placed in all possible orders like this. So for this shuffle product there, we have two natural algebras. So you could take all packed words, and that's going to form an algebra, and that's in Sage. But I want to take a slightly smaller set where I just take permutations of arbitrary symmetric groups. So these are just words that that contain every letter from 1 up to n exactly once. And I'm going to have two versions of this. One is where we allow infinite linear combinations, and one where we just take finite linear combinations. So that's our first algebra of the day. And then the second one is this familiar one of symmetric power series. So sim hat is just all symmetric power series over Z, and sim is those of bounded degree. So you can think of this as formal linear combinations of Schur functions, and this is finite linear combinations of Schur functions. So the forms that we place on these two algebras are as follows. For symmetric functions, we just make the Schur functions orthonormal. And for our algebra of permutations, which is either called like the free quasi-symmetric functions or the Malvenuto-Reutenauer algebra of permutations, we make we make the inverse of W, or we make inverse permutations orthonormal. So V inner product with W is 1 if V is equal to W inverse, and otherwise it's 0. So the theorem here, so this theorem actually contains a lot of content. If you dig into the details, it says, well, these two Hopf algebras, these pairs are dual Hopf algebras with respect to this form, which means that even though I haven't told you what the coproduct maps are, the products for these two algebras completely determine the coproducts, and this is sort of this for symmetric functions. This is this property that if you take a representation of the symmetric group, if you induce it or you restrict it, you see Littlewood-Richardson coefficients in both ways. So now I want to talk about combinatorial Hopf algebras, which means we want to talk a little bit about quasi-symmetric functions. So for compositions alpha, which are just going to be finite sequences of positive integers, we have this monomial quasi-symmetric function, which is just sum the corresponding monomial where we change all the indices by a translation. So we keep them in order. And quasi-symmetric functions are just linear combinations of these monomial quasi-symmetric functions. And we all know that, or it's a standard exercise to show that this is an algebra, a subalgebra of power series that contains the symmetric functions. And this is the only part in this talk where I'm going to assert something as a Hopf algebra that's not dual to something else to begin with. So this is a Hopf algebra for this specific coproduct that sends this monomial quasi-symmetric function to just the tensors where we split the composition in all possible ways and takes the tensor. So quasi-symmetric functions are fundamental in the following sense. So take a Hopf algebra H, and we just want an algebra morphism from H to formal power series, satisfying one tiny little condition, which is if we take this character map, which we call character, and we evaluate it, we get a power series. If we set t to 0, this should give us the same thing as evaluating our co-unit. Now again, I'm not going to say anything about units and co-units. For all of our objects, the co-unit is just set variables equal to 0. So in this setup, we have a Hopf algebra. We have this algebra morphism with this very mild condition, and then we view quasi-symmetric functions as a pair of this form, where we take the character to be the map that sends one variable to t and all the rest to 0. So you could rephrase this as sending any one variable to t and the rest to 0. And then we have this theorem which says that for each combinatorial Hopf algebra H with a character zeta, there is actually a unique Hopf algebra morphism from H to quasi-symmetric functions such that we have this little commutative diagram. If we first apply this morphism and then we apply this quasi-symmetric character, it gives the same thing as just evaluating our character zeta on our element of H. You got a question?
So the character has nothing to do with character from representation theory?
Yeah, nothing to do. Yeah. It's much more flexible. Yeah, it's essentially just a choice of algebra morphisms.
Yeah. Okay.
So we have this theorem. So this theorem, well, one, it sort of tells us that quasi-symmetric functions are somehow fundamental, and this theorem, you can write down what this morphism is, and it gives a way of constructing a whole lot of bases of quasi-symmetric functions. So here's the kind of first application of this sort of theorem is, for an n-letter word, we derive this composition where we just measure the maximal increasing subwords and record those as the parts of our partition. So in this word here, there's an increasing word 1, 3, 4, 6. So that gives us 4 here, and then 2, 7, 9, that gives us a 3, and then 5, 8, that gives us a 2. And then sort of the natural character or increasing character to evaluate on words is if W is strictly increasing of length n, then you just map it to t to the n, and you map every other word to 0. So this is sort of our interesting choice. And then if you go back and look at that shuffle, shifted shuffle product, this actually becomes an algebra morphism for this Hopf algebra of permutations. So it's a fun exercise. And so as a consequence of this theorem on the previous slide, there is a unique Hopf algebra morphism from this Hopf algebra of permutations to quasisymmetric functions that satisfies this relation. And in fact, by looking at the formula for this psi here, you can show that the two permutations have the same image if and only if their associated compositions are the same. And so we define L alpha to be the image of one of these permutations W for any permutation whose associated composition is alpha. And this gives the so-called fundamental quasisymmetric functions, which is denoted by F in Sage, but I'm more partial to calling it L. And then R alpha is going to be an actual element. So this is a quasisymmetric function. This is an element in our sum of our Hopf algebra permutations, where we sum over all permutations whose associated composition is alpha. So these are all the permutations that map to this L alpha under psi. And then one can show that these guys are another basis for QSym, and these guys are a basis for a subalgebra that we call NSym, non-commutative symmetric functions. And these two algebras, we can multiply these guys together, are dual Hopf algebras via the form that makes them these two bases dual to each other. And again, so the content here is this is not an obvious statement because this form defines sort of some coproduct, and then they're saying they're Hopf algebras means this coproduct obeys some compatibility condition, and then also it says that there is an antipode for this bialgebra structure. But this is sort of a classical, well-known theorem. Okay, so the things we've seen so far fit into this diagram of classical diagram of Hopf algebras. So the vertical lines here are these dualities via the forms that we've introduced. And then each of these inclusions is the adjoint of the surjection that is opposite. So if our inclusion goes from A1 to A2, and then our surjection goes from B2 to B1, and we have this kind of relation that determines, the one map determines the other. So we've already seen, so what is, so these, as I said, are inclusions. So what are these other maps? We've already seen that this is the map that sends a permutation, which is the basis of this Hopf algebra, to this fundamental quasisymmetric function. And then you can compute, so less trivially, you can compute that this top left map is sending this basis element R alpha to a certain skew Schur function, where the skew shape here is a ribbon of type alpha, which is best explained by an example. If alpha is 2, 3, 4, then we want to have 2 boxes here, and then 3 boxes here, and then 4 boxes here, and we connect them in this ribbon shape. So the relevant lambda and mu is like something like 7, 4, 2, and 3, 1, just to get this type ribbon. Okay, so regarding sort of Sage implementations, so all of the objects here, at least in the top row, ignoring sort of infinite, possibly infinite linear combinations, are in Sage in the combinatorial Hopf algebras documentation. What I'm calling permutations is called the free quasisymmetric functions. NSym is called NCSF, and the L alphas are the QSym.F basis, and the R alphas are the NCSF.ribbon basis. So all of this is sort of available for computations so far. Okay, so now I want to talk about a kind of K-theoretic generalizations of these algebras. So this arises in some work of Levin Piliovsky from a decade ago. So one way to tell this story is consider n by n complex matrices. It's just a set, it's a vector space, it's an algebraic variety, it's a lot of things. B is the group of upper triangular invertible n by n matrices. And there is an action, or a two-sided action of B on these matrices that we know from linear algebra. We can either multiply on the left or the right. Multiplying on the left does row reduction. Multiplying on the right does column reduction. So it's so a very pleasant exercise in Gaussian elimination is to see that the orbits of this two-sided action are indexed by partial permutation matrices. So you can cancel everything and end up with a matrix with just only entries 0 and 1, and at most one non-zero entry in each row and column. So just for simplicity, I'm going to restrict to the orbits indexed by full rank permutations, so I'm going to ignore the partial permutation part. So we take that orbit and then take its closure, and then I'm going to call that XW. So this is some kind of a matrix Schubert variety. And then I'm going to completely skip over all of the K-theory, the geometry details here, and just say, well, there's some way of identifying the K-theory ring of MIM matrices, the equivariant K-theory ring for the torus of diagonal matrices with the polynomial ring, and under this identification, the K-theory class of each of these orbit closures is some polynomial. So unlike the story where we tell about the flag variety, if you're familiar with Schubert calculus, there's no quotient by an ideal here. There's just literally K-theory class of this is an explicit polynomial. And maybe I've secretly made some variable changes just so things work out nicely. But this is sort of unambiguous. And this story is sort of from Knudsen and Miller's work. Okay, so these guys in this indecipherable letter, which is actually a G, are called Grothendieck polynomials. And they have a couple of special properties. So one, if you know Schubert polynomials, they look like Schubert polynomial plus higher degree term. And then they have these two stability properties, which are like as follows. So if you take a permutation W, which we view as a permutation matrix, and it's in Sn, and then you add an identity matrix in this lower right block, well, now you have a permutation in a larger symmetric group, which is indexing a different orbit closure in a larger set of matrices, and you can do it, and this is a different polynomial. But it turns out that these two permutations index the same Grothendieck polynomial. So it means that these guys are not even indexed by Sn, they're indexed by S infinity, or you can index them unambiguously by permutations of all the integers that fix the negative numbers. So that's one stability. And then the second piece of stability is that if you instead take your permutation and you add a bunch of fixed points to the beginning, so you put W in the lower right part of the matrix, well, as you do this and you make K larger and larger, two things happen. One thing happens is that, well, you're going to get a polynomial in more and more variables, but if K is large enough, then the coefficient of any given monomial will be constant as K increases. So it becomes a bigger and bigger polynomial, but if you print these out and you look at the first 10 terms, eventually they just are just the same, they don't change anymore. And then also, when K is large enough, these polynomials will be symmetric. Yeah, question?
Yeah, just to clarify, you said S infinity, which I think of permutations that only permute finitely many entries, but you said something.
Yeah, that would be the right definition here, yeah. So some kind of, I just mean S infinity is like the union of all the finite symmetric groups, nothing
thank you.
finitely supported permutations. So the second stability is that if you put fixed points at the beginning, then there's a well-defined formal power series limit, which is going to give you some symmetric function. And it's a symmetric function of unbounded degree, so it's here and not here, which could potentially create some difficulties. Okay, so how do we, so these sort of limits are the things we're interested in and give us some interesting Hopf algebras. So it turns out, so if W lambda is the so-called dominant permutation of shape lambda, then your Grothendieck polynomial is just a monomial. And so what are the dominant permutations? Well, the definition by example is you take your partition, you consider it, you put its Young diagram in a matrix, and then you arrange the ones in your for your permutation matrix of W, so that if you kind of draw these, if you cross out everything to the right and below those 1s, then you're only left with your desired Young diagram. And what we can do is define the stable Grothendieck polynomials as these limits that we saw on the previous slide. So this limit for just the dominant permutation of shape lambda. So it turns out that these guys are sufficient to span everything. G lambda is a Schur function plus some higher degree terms, and which means that they're automatically a basis for these unbounded degree symmetric functions. And these symmetric functions have some interesting non-trivial properties. So one is each GW is, well, it's spanned by these G lambdas, and it's even though these are unbounded degree symmetric functions, it's in a finite span with positive coefficients. And also, if you take any two products of G lambda and G mu, even though in principle it could be an infinite linear combination of these unbounded degree symmetric functions, because you might have to kind of correct terms at arbitrary degrees, it turns out that these products are also finite spans of other G nus with non-negative coefficients. So in other words, these guys generate a ring. So later, so this discussion doesn't tell you at all how to construct these polynomials or these symmetric functions. So later we'll talk about explicit generating functions over set value tableaux and reverse plane partitions that give these functions. And I'll just comment for the experts. So some authors like to work with these modified polynomials which involve a parameter beta, which is useful for kind of tracking degrees in various computations. I'm just implicitly setting beta equal to 1, and you can go between the two versions by some harmless variable substitutions. Okay, so I want to situate these Grothendieck polynomials, or yeah. So I want to situate these guys in in terms of some Hopf algebras. So generalizations of the Hopf algebra we saw earlier. So to start out, we define this relation on packed words that just lets you duplicate letters. So if you start out with 1, 2, 1, you can replace the first one by 2 1s, or the 2 by 2 2s, or the last one by 2 1s, and so forth. And you can just expand out these words. Or conversely, if you take any word, you can condense it. Whenever you have 2 equal letters, then you can replace them by just 1. And we're going to define 2 variations of this Hopf algebra permutations. The first is this bracket W means you sum over all packed words that are equivalent to W under this relation. So you start with a word, and you can just arbitrarily condense or double letters as you wish. This is going to be an infinite sum. And then the other version is we're going to take a quotient. So you're going to take the span of all differences, V minus W, where these are packed words that have this relation, and you're going to quotient, I guess maybe this should be not permutations, but all packed words, I think. Yeah, so this object should be slightly different. But both of these are going to be algebras for this shifted shuffle product. And both of them are going to have bases that are indexed by multi-permutations. This just means a packed word with no adjacent repeated letters. So it's almost like a permutation, but you can start repeating letters as long as they're far apart. So we're going to have these 2 bases, and we're going to define an inner product, or a bilinear form, that makes V and bracket W have value 1 if V is equal to W inverse. Or actually, I think this should just be equal to V. Since there's I don't mean inverse here, just a VW. And then you can make this statement. So these 2 Hopf algebras. So there's a lot of non-trivial things going on here, which is one, like you have to check that you can actually make well-defined products here, because their products of things are going to expand as infinite sums of things. But then with this form appropriately defined, these are going to be dual Hopf algebras again. So you can define a coproduct by duality, and then it'll satisfy some kind of compatibility, and then there's even an antipode formula that you can work out. So the other thing we want to do is, so we recall we have this increasing character, and it can be evaluated on these infinite sums because each of these infinite sums has only one term that is strictly, at most one term that is strictly increasing. Because if you have a repeated letter, then it's going to go to 0. So this is still going to send this sum to t to the length of w if w is strictly increasing, and otherwise to 0. And one can show that there's a unique Hopf algebra morphism from this larger Hopf algebra of multi-permutations to quasi-symmetric functions satisfying this relation. And again, the images of v and w will be the same if and only if they have the same associated composition. So you can define these multi-fundamental quasi-symmetric functions as the images of these w's for any multi-permutation. And then we can also take the sum in this quotient of all multi-permutations whose associated composition is alpha. And then this is another basis for QSym. And this is a basis for another subalgebra of this multi-permutations. And these are, again, dual Hopf algebras via this form that makes these two basis elements dual to each other. Okay, so these objects now fit into this modified diagram. These guys are the same. This is the same as before, but this is this other algebra or other subalgebra of this here, and we have these two new K-theoretic algebras of multi-permutations. Again, with dualities and inclusions and adjoint surjections. And the way these maps work is quite similar to the classical case, where the bottom right map we sends a multi-permutation to this quasi-symmetric function. I guess there should be double brackets around this w. And then this top left map sends R alpha to a certain dual stable Grothendieck polynomial G lambda mu, where this is the ribbon of type alpha, and I haven't defined what this is yet, but that will be on the next slide. And then there's this theorem of Lamp-Piliowski that says, well, each of these stable Grothendieck polynomials G lambda expands in a natural positive way in terms of these L alpha tildes. So all of this is kind of generalizing slightly the classical picture, but in fact, most of the algebras here are the same as the ones before. Okay, so now I want to tell you about the explicit sort of generating functions for stable Grothendieck polynomials. So recall that Schur functions are just generating functions for semi-standard Young tableau. So I'm not going to define what that is, but we have this formula like this. A set-valued tableau of shape lambda is as follows. So you take the Young diagram of a partition lambda, something like this, and you're going to fill each box by a non-empty finite set of positive integers. So this 256 is really the set 2, 5, 6. And you want the rows and columns to be weakly increasing in the sense that the maximum elements in one box is at most the minimum element of the next box. But we allow no repetitions in a column. So you can have a 2 repeated here and here, or you can have a 6 repeated these 3 times, but you can't have, if there's a 2 here, there can be no 2 in this box, and there can be no 6 in this top box, this bottom box. So there's a weight of this kind of tableau, which is just we count the number of times 1 appears, 2 appears, 3 appears, and so forth, and those are the exponents of our variables here. So we have x2 squared because there's 2 2's, x6 to the third because there's 3 6's. Okay, a reverse plane partition of shape lambda is another kind of filling of a Young diagram, this time by just positive integers, so no sets, just each box has 1 entry. And now everything can be weakly increasing. There's no condition about repetitions. So you can have 1s in a column, you have 2s in a row like this. So the non-trivial aspect of these gadgets is what their weight is. So here, the weight of a reverse plane partition is not formed by counting the total number of entries of a given type. What we do is for each I, we count the number of distinct columns containing I, and then that is the exponent, or that is the value in our weight vector. So x to the weight of this t is x1, because even though there's two 1s, they only appear in a single column, whereas x2 has exponent 3 because there are 3 columns containing 2. And x3 has just weight 1. Okay, so the first theorem here is that G lambda, which we already saw, is this sum over all set value tableaux of these weights. And then this, the second part, should be taken as a definition, because I think I left out one key fact. So the way these guys are defined is we have bilinear form on symmetric functions, which makes the sure functions orthonormal, and this is defined to be the basis that is dual to these G lambdas. So the inner product, or the bilinear form of G lambda and lowercase g mu is delta lambda mu. So you can make that definition, and then that's going to define these lowercase g's. And then it turns out to have this explicit generating function in terms of reverse plane partitions. Okay, so so this is sort of the K-theoretic generalization, and then now I want to talk in the last part of the talk about shifted analogs, which is sort of launching into to newer territory. So the way we're going to approach this is, well, I just told you these generating functions, and now I want to tell you kind of the natural combinatorial shifted versions before giving any algebraic or K-theoretic motivation. So the way we're going to modify these definitions to be shifted is, first, we're going to work with strict partitions, which means that all distinct parts. The shifted diagram of a strict partition is we take the ordinary Young diagram and we shift over row I by I minus 1 columns. So the first row is unchanged, the second row moves over by 1, the third row moves over by 2, and so forth. So in this shifted diagram, there's now these 3 boxes that are called the main diagonal. So there's this main diagonal, which is the always present. Okay, so what is a shifted set value tableau? So there's a couple kind of things that have changed before our previous definition. We're still going to fill this diagram by finite non-empty subsets. But now they're in this primed alphabet where you have 1 primes and 1s and 2 primes and 2s and 3 primes and 3s and so forth. So the way to understand this is 1 prime is secretly 1/2 and 2 prime is secretly 3/2 and so forth. So the prime is just subtracting 1/2. So they're in this order. And you're going to have a filling with subsets of these guys. They have to be weakly increasing again in the sense that the maximum element of one box is at most the minimum element of the next box. And then we have these conditions about repetition. So there can be no primed number repeated in a row, and there can be no unprimed number repeated in a column. So we can have 1 repeated in these 2 places, and we can have 3 prime repeated here, but we couldn't have a 3 in this box and a 3 in this box. The way the weight of this is computed is we count the numbers of 1s and 1 primes, and that is the exponent of x1. So there's a 1 prime, there's a 1, there's a 1, so you have x1 to the 3rd power, and then you have x2 squared because there's a 2 prime here and a 2, and so forth. And now, with this definition, we're just going to make these 2 definitions that look like our formula for stable Grothendieck polynomials. GQ lambda is the sum over shifted set value tableau, all of them. And then GP is the sum where we restrict to such tableau with no primes on the main diagonal. So this tableau would not be included in this sum because there's primes here and here. If we got rid of this 2, if we remove this 1 prime and we change this 2 prime to a 2, then the tableau would be included in this summation. So we have these 2 big sums. So to start out with, this is sort of an arbitrary definition. You might ask, why is this interesting? So here is what turns out to be true about these guys. So first off, if you know about sure P and sure Q functions, don't worry if you don't, then these guys look like sure Q functions plus higher order terms, and these guys are sure P functions plus higher order terms. So Ikeda and Naruse are the guys who first introduced this sort of definition of this formula, and they showed that these, as lambda ranges over all strict partitions, these are linearly independent symmetric functions. So we're going to let GQ, bold GP be the infinite linear spans of these two sets of functions. And then it turns out that these two spaces are both subalgebras of symmetric functions. So they're proper subalgebras. And more strongly, so Clifford Thomas Young showed that if these GPs generate a ring, if you multiply them, then you get a finite linear combination, even though a priori you would only expect an infinite one. And so Joe Lewis and I recently also showed that the GQs also have this property. So this was conjectured by Ikeda and Naruse, but it was sort of an open problem to show that these guys generate a ring. And then there's a way of interpreting these functions as stable limits of K-theory representatives. The highly abbreviated discussion, the main idea is instead of looking at two-sided B orbits on all n by n matrices, you could look at symmetric matrices or skew-symmetric matrices. Then your B group still acts, but the action is by like a conjugate transposition. So X goes to BX, B transpose. That's going to preserve symmetric and skew-symmetric matrices. So you get a family of orbits indexed by involutions in the symmetric group. You can take their closures. You can consider their equivariant K-theory representatives. There's some polynomials, and then you take some kind of limit, and you would get GQ and GP lambda. So there's some analogous discussion there. And then if you know about sure P and sure Q functions, you might know that there's a very simple relationship between these two, which is, or in other words, there's a simple relationship between the lowest order terms of GQ and GP, which is just a scalar. So it turns out, so GQ is a finite linear combination of GPs, but in a much less trivial way. So you may need negative coefficients, and there'll be several terms, and it was non-trivial to figure out what this is. Okay, so then that's one version of the story. Here is now the dual version. We still have a strict partition. So what is the shifted version of a reverse plane partition? So again, it's just a weakly increasing filling of this shifted diagram, but now we're allowed to use these prime numbers, and that's it. That's the only condition. This is all that we require. So you can have something like this: a lot of threes, a lot of 1 primes, a lot of 2s. Again, the interesting thing is how are we computing the weight of this very general object? And what you do is you count the number of columns containing I and rows containing I prime. You add those up, and then that is the exponent of xi when you do this evaluation. So in this example, there's 2 1 primes, but they only appear in one row. So x1 is to the first power. There's only 1 2, so it's x2. And then even though there's 4 3s, they only appear in 2 distinct columns. So you have x3 squared. And now the definition that we make is, well, lowercase gq is the sum over all of these shifted reverse plane partitions, and we have the same kind of signed weight as we did for the lowercase g's a few slides ago. And then GP lambda is the same sum, but instead of requiring no primes on the diagonal, we say every entry has to be primed. So that's kind of the curious condition here. So all diagonal entries in this reverse plane partition must be primed. You take this big sum. So here are sort of the interesting properties about these guys. So kind of dual to the uppercase functions, these guys have a highest degree term, which is a sure Q function or a sure P function, and then lower order terms. So these guys are actually symmetric functions of bounded degree. So we proved that there. And then both of these, if you take the span of these guys, they give you 2 subalgebras of symmetric functions. And if you define this bilinear form that makes lowercase gq or orthonormal to uppercase gp and lowercase gp orthonormal to uppercase gq, so this is some form. It is not the Hall inner product that makes Schur functions orthonormal. It's some different form. Then these algebras turn out to be dual Hopf algebras via this form. So again, this is included in the statement is saying that if you take the product structure constants for the lowercase functions, they tell you the coproduct structure constants for the uppercase functions and so forth. And I guess I should also say, so via this form, it gives you some coproduct, but the coproduct on these algebras is actually, it's the same one as on ordinary symmetric functions, if you know what that is. It's just sending a Schur function to the sum over Littlewood-Richardson coefficients. So these results are all things that follow from a conjecture, or a conjecture of Nakagawa and Naruse that is about Cauchy identities. But these are sort of the more concrete consequences of their conjecture, which we proved. Okay, so I can put all of these guys now in this bigger diagram of Hopf algebras. So the very last part, I just want to say, well, how do we motivate these combinatorial definitions algebraically? So we've already seen these K-theoretic Hopf algebras. We just defined these guys. And then there's these intermediate things. So this is going to replace symmetric functions, quasi-symmetric functions, and it's dual. So I haven't said what these guys are. So these peak quasi-symmetric functions are going to have certain bases k alpha and k bar alpha, and they're going to be indexed by peak compositions, which means every part but the last is at least 2. And then, well, I'll tell you what these are in the next slide, but then you can show that these GPs and GQs expand positively into these two bases in an explicit way. And then these Hopf algebras, these peak Hopf algebras, are free as algebras with some generators, pi q and pi p, and these top maps here are going to just map pi q to gq and pi p to gp when your partition has just one row. And I should also say, so if we worked with scalars that are q rationals instead of integers, then we would only need one side of this diagram because the q and the p versions of everything would coincide if your scalars were slightly larger. Okay, so how do we get these peak, multi-peak quasi-symmetric functions? So first, for an n-letter word, we're going to have this new composition which gives the lengths of the maximal v subwords. So in this example, you have 3, 2, 1, 2, 3, 4. That's of length 6. And then you have 3, 2, 1, 2, 3. That's of length 5. And then the rest is just 2, and that gives you a length 1. So recall that we had this character, this increasing character, that sends a multi-permutation to its length if it's strictly increasing. You could also consider the decreasing character, where you only send w to t to the n if w is this, everything is in strictly decreasing and everything else goes to 0. And you can, by the same kind of formal stuff as before, there's a unique morphism for this decreasing character that sends these multi-permutations to quasi-symmetric functions. But it turns out that the basis of objects you get is exactly the same, just the indexing is different. So if you want to get something new, we will combine these two characters by this natural kind of product that exists for linear maps from a Hopf algebra to formal power series. We compose the coproduct with the tensor of these two with the product. And then what turns out to be true is that, well, there's a unique Hopf algebra morphism that satisfies this relation with this character, and it sends multi-permutations to the same thing if and only they have the same peak composition like this. So we can define these k alphas to be the images of multi-permutations under this unique morphism. So the k bars, the easiest way I can define them in this presentation is just indirectly by some relation like this. So there's some upper triangular matrix that relates the k alphas and the k alpha bars. And we let these two spaces be the infinite linear spans of these two families. And then these both are subalgebras of quasisymmetric functions. And the dual version is we now sum over all W in this quotient algebra that have the same peak composition, and then there's another version. This is just some dual expansion to this. These guys are bases for two subalgebras, P and Q here. And then the theorem is that, well, these algebras, these two pairs of algebras are dual Hopf algebras via the forms that make these bases orthonormal to each other. Okay, so let me just conclude then with kind of some open problems, or what's known and what's not known about this whole discussion. So one thing, from 20 years ago, we already knew that the Schur expansion of G lambda and lowercase g lambda. And we also now know, I can tell you explicitly how to decompose GP lambda into stable Grothendieck's. And then there are explicit Littlewood-Richardson rules that tell you how to expand these products in the relevant bases for the capital G's as due to Buch, and then Clifford Thomas Young have something that deal with the GPs. And then you can write down antibode formulas for everything here in terms of sort of conjugate functions. But I haven't really talked about antipodes at all in this presentation, but everything, the antipodes can be computed. Things that are not known is, like, for example, do the GQs even expand positively into the G mu's? So presumably they do, but it's not known what that expansion is. I don't think it's known the expansion of these dual functions into lowercase g's. I don't think there's Littlewood-Richardson rules to compute any of these products. I'm a little bit uncertain about the lowercase g's, but about the shifted versions, I think that's completely unknown. And at least some of these objects would be natural things to implement in Sage. So for example, all of the lowercase functions are bounded degree symmetric functions, which would not be too hard to just implement. And then one could be able to experiment with try to figure out what these coefficients are. And then maybe there's also a way to deal with these unbounded degree symmetric functions, though it's a little bit more thought's probably needed. Okay, so thanks. That's where I'll stop today.
All right. Do we have any questions for our speaker?
Probably you have explained it. Can you explain me what do you mean by weakly increasing filling?
So the main idea is, let's see, what's the?
I think 15 or something.
So something like here. So we have adjacent boxes. So our boxes are going from left to right and from top to bottom. And the weakly increasing just means the maximum elements in one box is less than or equal to the minimum element in the next box.
No, along the columns?
Yeah, along the columns too. So if you just read the word here, you say 2, 3 prime, 3 prime, 3, 4, and that's sort of weakly increasing.
Okay, fine. So along the column, it's not strictly increasing. It's weakly along the column also.
Yes. So the condition is that everything is weakly increasing, but you can repeat primes. So 3 prime can be repeated, but you're not allowed to repeat like 2 or 3 or 4. Only repetitions on a column can only be prime numbers, and repetitions in a row can only be unprime numbers.
No, even in the previous diagram, you have repeated 1, 1 twice.
This here, right?
Not here. The previous slide, maybe.
Here.
Here.
Yeah. So this is the plane partition. So it's different conditions. So we have tableaux and then we have plane partitions.
Okay.
So the plane partitions have less conditions. They're just weakly increasing, and you can repeat anything you want.
So, just one more minute. And you have a lot of arrows between lot of Hopf algebras.
Yeah.
What these arrows are? These are functorial or?
So yeah, so it's all these arrows. So many arrows, but most of them we can figure out without any information. So these vertical arrows don't really mean anything. They're just indicating there's a duality. These arrows are all inclusions. So everything here, this is defined. By definition, this is contained in here. I guess the way I present this is not obvious that it's contained in here. Or it follows from this theorem here, that this is actually contained in here, and this is contained in here, and so forth. So the only thing that's ambiguous here is what are the surjections. So in principle, those are determined by, if you know the bilinear form and you know the inclusion, then it's the adjoint map. But in these particular cases, these maps are again sending, so this is sending some multi-permutation to some k alpha. So it's this unique map here. This psi, which is the unique Hopf orthogonal here, is in both. These two maps are both psi, and then these guys are described here by these projections. So the surjective maps are determined by duality by the inclusions. So that's kind of the canonical part.
Okay, thanks.
Are reverse plane partitions and set value tableau and so on FindStat?
So the next question is, why have you defined shifted set values tableaus the way you have done? Like, is it something that comes naturally from the definition of set value tableaus?
So let's see. So the definition, I guess, comes from this work of Ikeda and Naruse. So they defined these guys in a geometric context, talking about K-theory, and then they proved this theorem that said there is this explicit set-valued formula. So there's other formulas, I guess, also for these functions. This one seems to be the most concrete. You can define it on one slide, and then in principle you could start computing what these are. But this is just one, the most self-contained definition you can give. But there are other formulas.
Okay, but like there's no relation between set value tableaus and shifted set value tableaus, right? I mean.
Let's see. So what you can do. So you could define one relation that you could say is, instead of working with shifted diagrams, you could just do the same conditions here on unshifted diagrams. So again, you have finite non-empty subsets of these primed and unprimed things satisfying these conditions. So that's like and then if you consider G lambda and you mapped it to this other generating function that would be over the unshifted sort of set value tableau satisfying these conditions, well, you can show that's actually a Hopf algebra morphism from symmetric functions to the things spanned by GQ. So that you can make some sense of it. There's some kind of this operation is sometimes called like superfication or something. There's some natural operation that kind of turns set value tableau into kind of a shifted set value tableau, but it's not so simple. Yeah.
Okay, thanks.
All right. What other questions do we have?
A rather basic question. So can you say something about what it buys you if you know that two Hopf algebras are dual?
So what I like about this in this presentation is just that I can only talk about algebras, and then I can say they're Hopf algebras. If you have this pairing, then you can just, without referring to any coproduct or any dual identities or any compatibility, you have an algebra, you have another algebra, you have a pairing, and then saying they're Hopf algebras is equivalent to just what I showed in the earlier slide. So but beyond that, like what do you get? I mean, algebraically, right? They're equivalent objects. You should only have to work with one over the other. So one thing that happens is, so sometimes it's easier to prove things when you're working with one or the other. So for example, here, well, there's kind of these open questions about multiplying these GQs. And by duality, that's talking about evaluating like coproducts of these guys. But these guys are bounded degree symmetric functions. You can write down all the terms. And if you kind of consider, and sort of nice things, so it can be easier to do with certain arguments because maybe you only have to think about a finite set that is infinite for the other version. So that's sort of a useful thing that happens.
What other questions? Well, maybe I'll do one quick comment because you said the g lambda, the little g lambda times g mu, but I believe Buch in his paper talked about the coproduct and had coefficients for that for the big G's. So I would,
okay, yeah.
Basically from what you were just explaining, I
yeah,
believe
in that case, yeah. I'm not completely certain about this. Yeah, but yeah, that would be solved. This case would be solved if that's true. Yeah.
Maybe I'll also ask one more quick question. Do you know how anything about skew shapes and how they and those expansion coefficients in terms of the straight shapes relate?
Okay, yes. So so all these tableau generating functions, there are skew. You can make skew versions where whatever it is, like, instead of filling the shape, you could skew out some part and then have the same definition. So the following are equivalent. If you can tell me a coproduct formula, then you can also compute all of the skew expansions. So they're equivalent problems. So in fact, one way of writing the coproduct here, the coproduct of this lambda is sum over GQ mu tensor GQ lambda slash mu. So if you can tell me what the coproduct of this is in the basis of tensors, then you can also tell me the skew expansion of any of these. So they're equivalent problems.
And I thought that you got different coefficients when you do that for the big G's.
So the big G's, yeah, very, very good. So for the big G's, there's this issue. Well, you have to know something about the coproduct and the symmetric functions, but there's this issue that you have to do this special skewing where you might have some extra boxes left over because things are set valued. So it's like if you divide the numbers here between things up to 2 and things above 2, then but that special skewing is a finite linear combination of the ordinary skewing. So again, in principle, you can compute the.
And do you understand that for the GPs and the GQs, what that expansion is?
No.
Okay.
Yeah. That is the equivalent. This problem about so it's like that is sort of included in. If you could do that, then you could solve these last two problems. So.
Okay. Any additional questions? All right, let's thank our speaker again.